And we are now recording. Let's start from the current slide, which we're not there yet. Okay, let me even turn on the projector. Okay. Trying to think if there are any announcements. I guess I should say this one, and don't believe it affects any of you at all, and I don't believe anyone who's been coming to class it affects. But they have finally removed all the unpaid students from the rolls, okay? And the only unpaid students we had in here, as far as I know, were the three people who we've never seen, okay? So let me get their names off of here. And, all right. I think all the rest of you are still there yet. I believe there were 16 paid. And there were 19 originally, but those weren't there. So, anyway, y'all are all in good shape. But if you're in any other classes with people and they've noticed their names are not on the roll anymore, they're not being called or something, let them know. Check with Financial Services or Business Office somewhere. Find out what the deal is with the payment. Something has not been registered. All right. Any questions before we get started today? All right. We're in 3.3, just finishing that, but if you'll note, the slide here is 3.4. Well, the reason for that is the last example in 3.3 wasn't on the slide set for 3.3, so I went on and started with 3.4 here. All right. Here is example 5, if there are no questions on any previous one. Neglecting air resistance, the path of a projectile that is propelled at an angle theta is given by this formula. Let me get my pen set up. Goodness, this is bothersome that the eye that I operated on is so itchy today. I hope it doesn't mean anything. Y is equal to minus, now my computer started off just fine this morning and now it's doing flaky stuff, so I've got to watch that, is equal to negative G secant squared theta over 2 times V naught squared, all that's times x squared, plus tangent theta times x plus some number h. Okay? Now, that's good for all thetas. They say less than or equal to 0, which the equal doesn't make a lot of sense then. Well, I guess it does. Less than theta, less than or equal to pi halves. And really the equal there doesn't make lots of sense either. Now, y here is the height at any time, at any position x. I'm sorry, the time is not in this. Any position x. Okay? X is the horizontal distance you are from wherever you launch the projectile. Okay? G is the acceleration due to gravity in whatever units you happen to be. That's the G there. Your theta, of course, is the angle that you are projecting at, propelling it. V naught, V sub 0, is your initial velocity that you're given the object, and h is the initial height. Okay? Now, they say that equation is derived in section 12.3 if you're interested in going there. Now, what they're going to do is let G equal 32 feet per second squared. Okay? So we're in the U.S. customary system. All right. Let me back off just for a moment. The reason I said to have theta equal to 0, to have that equal sign there, is really a fairly meaningless situation. Because then you're firing the projectile horizontally, and the y is how high it's going to go. Well, it can't go any height, okay, because you're firing it horizontally. So when x is equal to 0, meaning you're at the original position, then that's you're at 0 height, because the tangent of 0 is 0, and the original height is 0, okay, or you're at your original height. And then anything after that, it's dropping. So I guess that makes sense. If you're up on a mountain and firing horizontally, then it will be dropping. So I guess that if your initial height was greater than 1. So I guess that could make some sense, okay? Now, the theta equal pi halves, I mean, you're firing directly overhead. Now, unless you hit something on its way up, you better move, because when it comes back down, it's going to hit you, okay? So I wouldn't be firing a projectile at an angle pi halves to begin with, okay? So that's sort of, in a sense, ridiculous as well. But that will give you the correct formula, but it's just sort of a nonsensical thing to include those equal signs there. But they did, and it's all right. It doesn't take anything from the problem. It just doesn't make any too much physical sense. The V0 initial velocity, we're saying, is 24 feet per second. And that's a this is a projectile propelled, and in the illustration on the margin there, you see it's a guy shooting a basketball. Well, that might be a pretty reasonable assumption at a velocity there, okay? So 24 feet per second. And h is equal to 9 feet. Now, I've never shot a basketball from an initial height of 9 feet, because I can't jump that well, okay? But if this guy has really got a great jump shot and he's pretty tall, his initial height could be 9 feet, okay? Now, what value of theta will produce a maximum horizontal distance? Now, the key words in the very beginning are neglecting air resistance. With that in there, you can almost, not quite. I was going to say you can almost tell the answer to that one, but it will be a little bit different, namely because of that initial height of 9 feet. So anyway, what we're going to do, let me draw a quick picture here, okay? And you want the maximum horizontal distance. And y is the height. So you're trying to maximize the x, okay? It's a little bizarre, but it's okay. Okay, and he's shooting the basketball. He's jumped out into the air, and he's shooting the basketball from over his head. Okay, so his arms are up here. So it's launched here. So this is 9 feet. Initial, that's his h. Okay? Initial velocity, we don't know in what direction, is going to be 24 feet per second. And of course the acceleration due to gravity, which is pulling it downward, is 32 feet per second squared. And by the way, that's why the minus sign is in front here, because the g is always negative. Okay, the g is positive, but the acceleration is always negative. The gravity is always pulling it downhill, okay, toward the center of the earth. That's why the g is, that first term is a negative term. Okay? Now, okay. So we're going to plug and chug. We're going to plug the numbers in first and see what we get. Y is equal to, maximum horizontal distance. Okay? When he's shooting the basketball, sure, we want it to go into the hoop, if that's what he's doing, and that's up here somewhere. Here's the backboard, and there's the hoop here. But that's not what we're asking. Maximum horizontal distance would be how far it goes before it hits the ground. When it hits the ground, the y is 0. Okay? So this isn't necessarily shooting a basketball. That would stop there. We're throwing something. And when it hits the ground, it's going to be y is equal to 0. Okay? So let me add that up here. They had it in the book. I just didn't do it. Y is equal to 0 when it hits the ground to give the maximum height. So here's what we're looking for. We're looking for x max. Okay. All right. So plugging these values into the formula, we have 0, that's your y, is equal to minus 32 feet per second squared. I'm going to leave off the units because they'll just get really messy there. Secant squared theta over 2 times 24 squared. Someone with a calculator, square 24, I probably can do it in my head, but I don't want to, times 2. So 12 squared would be 144. And then multiply that by 4 and you get 664 maybe. And double that, 1288.
Say it again.
Okay, 24 squared times 2. Second? 1152. Sounds reasonable. My calculations obviously were off some. Okay. Times x squared plus tangent theta x plus 9. Okay. There is our original equation here. Okay? Now you can simplify it some. They claim, and I think they're probably right, that 32 will go into 1152. See if you get that it does. Because here, finally, holding up the bottom part of the alphabet. Okay. Is 36? All right, that's exactly what they got. So that'll go into that 36 times. So there's our equation. Okay? Minus secant squared over 36 x squared plus tangent x, tangent theta x, plus 9 is equal to 0. I've got 0 on the other end. Okay. Now, so far I haven't seen any calculus in this, okay? This is all sort of physics and, following formulas and that kind of stuff. So, what we've got here is a quadratic equation in x. So, they say use the quadratic formula. Don't believe this one will factor, folks. Quadratic formula. And here's your A, here's your B, and here's your C. So this says x is equal to, anyone remember how quadratic formula goes? Negative b, so that would be a minus tangent theta, okay, plus or minus the square root of, and then the b squared would be tangent squared theta, minus 4 times a, well that's a minus, so that becomes a plus, and if you do 4 times this over 36, you lose the 4 and that becomes over 9. So I'm going to go on and take care of that because I have so little room at the end of the board here. So that's going to be secant squared theta over 9 times c, which is a 9, which wipes out that 9, okay? So, tangent squared theta plus secant squared theta. Is that an identity? Sort of smells like one. Let's see. I know that tangent squared theta plus 1 is equal to secant squared theta. Oh, no, it's not. Okay? There's no way you can get that. Have I done something wrong?
Yeah.
What's that? Okay, yeah, we'll get there in a minute. I was just trying to see if anything panned out, and I don't see that it does. So no, in the book it's still there. Okay, and I did multiply by 9, but I wiped it out because you had a 9 in the denominator. Okay. Now all that divided by 2a, which is a minus secant squared theta over 18. Okay, that's 2 times a. Now that looks like a big mess, doesn't it? Let's see if we can clean it up just a little bit. Let's flip that over in a sense, and you have 18 tangent theta x is equal to and then we have a minus or plus. I'm going to do it like that, though I don't think it really matters. The square root of tangent squared theta plus secant squared theta. Okay, and all that's divided by secant squared theta. Okay, now let's see what we got. Okay, now they're going to do something clever here, which is a very good idea. Change everything to sines and cosines. So this is going to be, oh, I did mess something up here. There's an 18 here also, because when you multiplied through by that, you got them both. Okay? Now, it's going to be 18, and that'll be sine over cosine. Aggravating to keep flipping like that on me. What I'm going to do is get rid of that denominator up there, because that's going to be in my way when I'm writing. So people who come in late, that'll not make any sense, but I'll put it back in if I need to. Now I'm going to put minus or plus, and again, I don't think it matters that you have this like that, but it doesn't matter which order you do. And we have an 18 here, and we have a square root of, this would be sine squared theta over cosine squared theta, that's tangent squared, plus, and your secant squared is 1 over cosine squared theta. All that's under the radical, and all this is divided by 1 over cosine squared theta. Now, notice here you have a square root, you have a common denominator of cosine squared theta under the square root. So you can pull that out of the square root as just a 1 over cosine theta. And you have a 1 over cosine theta here, and you have a 1 over cosine squared theta there. So this one will wipe out one of those, and these will also wipe out one of those. So you're rid of the cosine. So now you got 1 over cosine in the denominator. You can flip that over and make it 18 times sine theta cosine theta plus or minus or plus. I don't really think it matters. I'm going to go back to plus or minus. The square root, or 18 times the square root of sine squared plus 1. Okay, sorry. That's messy. I'm going to have to start erasing stuff in a minute. That's what your x is. Okay? As a function of theta. Okay, what do we do with that? Let me make sure I've got everything right. This one was multiplied by that cosine 1 over cosine 2, so it has a cosine in it as well. So I think I'm going to erase a bunch of this. We don't need that anymore because that wasn't helpful. I'll keep my original problem because we may need to come back to that. I don't think we need those anymore, so let's get rid of those. That was our initial conditions, what was given in the problem. Oh, I was going to keep my picture, sort of. I don't know if I need the picture or not, but I'll keep it anyway. And let me correct this at the bottom. I'll come back and finish erasing in a minute. I just don't want to erase what I need. X is equal to 18 times cosine theta. That's common to both terms. And you have here sine theta plus or minus the square root of sine squared theta plus 1. Okay. That's what your x is equal to. And that's what they got. They wrote it, well, pretty close to the same. Oh, except for one thing. They took out the minus sign. Now, why did they do that? Okay? Well, let's think about this a minute. The square root of sine squared theta plus 1 has got to be greater than sine theta, right? Because the square root of sine squared theta would be sine theta, right? So you add 1 to it, that's going to be greater than that. Well, if it's greater than that, and when you have the minus in there, that gives you a negative number here. That means the x is behind you. So you're shooting the basketball and it winds up back there. I'm a pretty bad shot, but most of the time that doesn't happen even to me. So I think we can legitimately lose the minus sign there. So I'm going to do that right now, okay? Let's lose that minus sign right there. Okay. Now this makes sense, sort of, okay? And this tells you the reason we did that is because x is greater than or equal to 0, okay? In other words, we're not shooting behind us, okay? The horizontal distance that you're going, it's got to be in front of you. We're shooting that way, okay? That's just a practical thing. Now, at that point, you need to find the value of theta that produces a maximum value, and it says applying the first derivative test would be very tedious. No kidding. So they say use technology to do it instead. Okay. So they punted on it. And this is basketball. Okay. If you're trying to take the first derivative of this, which is doable, That is a mess. It's a product rule of this times that. This part of the product rule has in it, simple thing here, but then a really awful chain rule issue here. That would be an absolute mess. So rather than going through all that agony, they just say, plug it into a graphing calculator and do different values and see which maximizes. What a whip out they did. And they said it comes out awfully close to 45 degrees. Okay, no, wait. Wrong. I was going to say it's not. Okay. What it comes out to is about 35 degrees. If you were not doing from an initial height of 9 feet, then the maximum would be reached at 45 degrees. That would be my first. But since your initial height is up here, you can shoot it a little flatter and get it to go a little bit further. Okay? And sure enough, that's what they did. And they say it's about 35 degrees. Okay? Of the 3 paths shown. Okay? They said it actually comes out 35.3 degrees. Okay? And that's just using technology. So I'm sort of sorry we wasted that much time on one that's not, you can't calculate anyway. But it does show you, in real life, sometimes all these little things and stuff, they work great for very controlled problems. Real life is messy, and quite often you'll have to use an approximation. So homework exercises here. I think I've assigned most of these before, but let me make sure you got them. Number 3 is a Calc Chat. Any of the odds 5 through 9, they're all at Calc Chat. 5's at Calc View. Any of the odds 11 through 17, they're all at Calc Chat. 13's at Calc View. Any of the odds 19 to 39, they're all at Calc Chat. 21's at Calc View. Any of the odds 41 to 47, they're all at Calc Chat. 41's at Calc View. Any of the odds 49 to 53, they're all at Calc Chat. 55's at Calc Chat. You can think about doing any of the odds 57 through 61. Excuse me, they should all be at Calc Chat. You can explore doing either 63 or 65. They should both be at Calc Chat. And also either 67 or 69. They should be at Calc Chat. 71's analyzing a critical number. It should be at Calc Chat. You can think about doing 73. It should be at Calc Chat. Then do any of the odds 75 through 79. They should all be at Calc Chat. In one of my other classes, I have a guy who's in biological systems engineering. The trachea contraction, which is number 79, might be of some interest to him. I don't know if any of the others of you are going to biological applications, but that would be maybe an interesting one there. 81 or 83 should both be at Calc Chat. 85 should be at Calc Chat. 87 or 89 should both be at Calc Chat. And then true false, any of the odds 91 to 95 should be at Calc Chat. There's a couple of proofs at the end. 97 or 99 are both proofs. If you want to look into those, they should be at Calc Chat. The Putnam challenge, I don't know if it's at Calc Chat or not, but if it is, you could look at that if you're that interested. Okay? And there's a little thing called a section project that if you want to look at that, you certainly can too. I don't believe that's at Calc Chat. So now we're ready for, I'm going to clear the ink off here. Anyone need this any longer? All that work and we couldn't actually do a derivative. Okay? So let's clear that and back up to the beginning here. And here we have applications of differentiation. That's chapter 3. And we just did do the guy shooting a basketball, but we didn't completely do the guy shooting a basketball. So anyway, we'll go 3.4 are concavity and the second derivative test. 3.3 was dealing with the first derivative test, and those were extrema and the first derivative test. Now we're doing concavity and the second derivative test. So our objectives here: determine the intervals on which a function is concave up and on which it's concave down. We find any points of inflection of the graph of a function. New concept there, I mentioned it earlier. And we'll apply the second derivative test to find relative extrema. Hey, wait a minute, we've already done that, right? Well, the second derivative test makes it easier. A lot of the grunt work we had to do with the first derivative test, all those test points, second derivative test eliminates most of those. Okay? So, what in the world is concavity anyway? Any idea? What word do you almost see there? Concave, what does that mean? I can remember some teacher way early saying it's not like the mouth of a cave. It curves inward. That's concave. If it curved outward, that's convex. Lenses are either concave or convex, inside and outside. Okay? So a concave is something that curves like this. So what we're interested in now, you've seen that locating intervals on which a function increases or decreases helps to describe the graph. In this section, you'll see how locating the intervals on which f prime increases or decreases can be used to determine whether the graph is curving upward or curving downward. That's the concavity. So here's a definition of concavity. Okay? Let f be a differentiable function, has to be differentiable, on some open interval I. The graph of f is concave upward on I when f prime is always increasing on the interval. Okay? It's concave downward on I when f prime is always decreasing on that interval. Okay, now wait a minute. When you had a function increasing, what did you know that had to be true about it? Function increasing. Its first derivative was positive. Now, if you have f prime increasing, guess what that suggests? The second derivative has to be positive. Hey, we've just figured out what concave up means. The second derivative is positive. Okay? Wow. And concave down, second derivative is negative. Now, before the book gets there, here's an example. Following graphical interpretation of concavity is useful, they say, and I think it is. Let f be differentiable on the open interval I, that was required. If the graph of f is concave upward on I, then the graph of f lies above all of its tangent lines. Now, I've never thought of it this way before this book, but it does make sense. Notice the tangent line here, the graph is above it. Tangent line here, the graph is above it. Tangent line here, the graph is slightly above it, but still above it. So what this means, the f prime, the slope of the tangent line, is increasing, trying to keep up with the function. So, and as we just said, that means the second derivative is positive. The book hasn't gotten there yet, but that's where we're headed. The graph of f lies above the tangent lines. And concave up. If it's concave up, it'll hold water, right? Okay, that's another way to think of it. Concave down, it's spilling the water, okay? Think of a bucket or something like that. You hold it upright, the water's in there, turn it over, and it falls, spills out. All right. Here's Ashley. All right, some help holding up the latter part of the alphabet there. Okay. Now, let f be differentiable on open interval I, and if the graph of f is concave downward on I, then the graph of f always lies below all of the tangent lines. There's the tangent line here, the graph's below it. The tangent line here, the graph's below it. Tangent line there, just slightly, but still below it. What does that mean? That the function is turning downward because the tangent lines always are having to They're always above it and turning down, trying to keep up. So what does this mean? It's concave downward. The first derivative is decreasing, which we know means the second derivative is negative. Okay. Does that make sense? All right. To find the open intervals on which a graph of a function f is concave upward and concave downward, you need to find the intervals on which the first derivative is either increasing or decreasing. Okay? Now, here's a function. F of x equal 1/3 x cubed minus x. There it is. They've drawn it for you. Now, I can look at that and say, I can tell up here that's concave down. I can tell right here it's concave up. I'm not absolutely certain I can tell exactly where it changes from being down to up because the slope of this is changing so slowly. Happens to be right there, but we don't know that yet. Okay? So, how we tell is guess what we do? Let's get Jesus' answer. Take a derivative. Very good. What's the derivative of f of x? Is it that hard? Derivative of f of x. Here's f of x. What's its derivative? Again? X squared minus 1. Right. Okay. Oh, there, you read it down there, didn't you? You didn't even think about it. No, I'm just kidding. Okay. All right. Concave downward on the open interval negative infinity to 0. Why do we say that? Okay. Because when this first derivative is negative, when is that negative? Okay? Not the first derivative is negative. That means it was a decreasing function. It's when the first derivative is decreasing. Okay? Now what they're doing is looking at the graph. Well, yeah, they graph this. X squared minus 1. Well, that has zeros at minus 1 and plus 1, and it's when x equal 0, that's equal to minus 1. That's a good old parabola here. So your first derivative is decreasing from negative infinity up to 0. At 0, it stops decreasing. After that, it's increasing. So it's the first derivative is negative, meaning it's concave downward from negative infinity to 0, and then it'll be concave up from 0 to positive infinity. The first derivative is increasing here. So the function here, concave down everywhere from negative infinity up to 0, but at 0 it flips and the first derivative starts increasing. It is positive after that, so your it's concave up from that point on. Okay. Now, what they did based on the graph, okay, they didn't do any analysis of this, they just based on the graph. Where is this? Decreasing. Looking at the graph of that, it's decreasing from negative infinity to 0. All right. Similarly, the graph of f is concave upward on the interval from 0 to positive infinity, because at that point, its first derivative is positive. Okay? So therefore, the first derivative is increasing from 0 to positive infinity. Now, the other way, I'm not doing the way the book does. Here, the tangent line's above the graph, so therefore it's concave down. Here, the tangent line is below the graph, so therefore the graph is concave up. I don't think of it in that way, but that's what the book suggested. All right. The next theorem shows how to use the second derivative, I've already been telling you about it, of a function f to determine the intervals on which the graph of f is concave up or concave down. And we've already said it without, well, we said it, but they suggested it, we said it. If f is a function whose second derivative exists on the open interval I, if f double prime, second derivative is greater than 0, all right, Reginald's here. All right, good deal. What else? If the second derivative is positive, greater than 0, for all x's on that interval, then the graph of f is concave upward on that interval. However, if f double prime, the second derivative of f, is always negative for all x's in that interval I, then it's concave downward on that interval I. Okay? Test for concavity. No, concavity. I always want to put an extra syllable in there that doesn't belong. Concavity. Okay, now to apply theorem 3.7, locate the x values at which f double prime is 0. Hey, this sounds familiar, doesn't it? Or where f double prime doesn't exist. Okay, now let's go back here for a moment here. We said that f is a function whose second derivative exists on an open interval I. Well, if it doesn't exist, it's neither concave up or concave down at that point because it has to exist. So that might be a suggestion of where the you might have a change of concavity. The other place is where the second derivative is equal to 0. Does this sound familiar? These are the very tests we used for the first derivative to determine whether the function was increasing or decreasing. Okay? So, same deal, except this is for concavity. Locate the x values for which f double prime is 0 or doesn't exist. We use those x values to determine test intervals. Here we go with test intervals again. Finally, the test assign of f prime in each of those test intervals, and then you'll know whether it's concave up or concave down. At 0, it's neither, okay? Where it doesn't exist, it's neither. On one side or the other of those values, it may change or it may not change. That's what you've got to test. Okay? So, let's do it. Determine the open intervals on which this graph is concave up and concave down. So what you reckon we're going to do first? I put the equal sign there trying to suggest something to you. Now you could do it without this suggestion, but I like it better to do it. Okay? Say that one more time. Yes, I like it. We'll rewrite this as 6 times x squared plus 3 to the minus 1. And then what are we going to do? You don't have to do it this way, but this is my preferred method. What do you do then? What's the good Jesus answer? Take a derivative. Okay? So your f prime of x is equal to, using this form. Is that helpful or not? Negative 6 times x squared plus 3 to the negative 2 times 2x. Perfect. Okay, get out of there. Okay. Now, let's clean that up a little bit. Okay, and that would be a negative 12x is in your numerator, and in your denominator is x squared plus 3 squared. You don't have to go back to rational expression, but it seems like it may help. In fact, no, I don't want to do that. I forgot we're doing a second derivative, so let's leave this as minus 12x times x squared plus 3 to the minus 2. Sorry, wish I hadn't done the other one. Because what are we going to do next? We want the open intervals on which the graph is concave up or concave down. We're going to take a second derivative, f double prime of x, and I would just as soon use that form there rather than this one. You could use this form and use the quotient rule, or use this form and use the product rule. About the same difference. I just tend to like product rule a little bit better. It doesn't have as many sign changes, so I hope not to make as many sign errors. Okay, that's where I tend to make errors. So let's do that. What would that give you? Whichever one you want to use. Which are you going to use? Say again? Okay. Okay. All right. You're doing it right, but I'm afraid we're going to mess up somewhere there. Let's do the product rule a little more succinctly, okay? Let's do this one first. Here are the two functions, u and v, right? So which you want to do first? And you may have been doing it. In fact, I think you were, weren't you? Yeah, she was. Okay, now let's see what she's doing. You get the minus 12x times the minus 2, which is positive 24x. What's the next part of that? X squared plus 3 to the negative 3. And then one more part, times the 2x. Okay. There's the first times derivative of the second. What follows that? Normally be a plus, but this is a minus here, so we'll do a minus. We may have to change back to a plus, but at least it starts off being minus because the whole thing was minus. What? Derivative of the first is just 12 times x squared plus 3 to the minus 2. Okay? Now we want to clean it up a little bit. All right. This is going to have a 48 x squared, right? Over x squared plus 3 cubed. Do you agree? Yay or nay? Okay. The next one's going to be a minus. This is simply 12 over x squared plus 3 squared. No real nice way to combine those unless we get a common denominator, which means we're going to have to multiply this denominator by another x squared plus 3, which means we're going to have to multiply the numerator by an x squared plus 3. Okay, let's clean that up a little bit. And what we have then is, numerator here is 48 x squared minus 12 x squared minus 3, because that minus changes both of those signs, all over x squared plus 3 cubed. Okay? Well, let's combine these two together and give you 36x squared minus 3. We can fix that a little bit. I'm rapidly running out of room here. That second derivative is equal to 36x squared minus 3. Let's factor out a 3. And it's 3 times what you have left? $12x squared minus 1. over x squared plus 3 cubed. All right. Now what we want here is to determine the open intervals on which the graph is concave up and concave down. Okay? What that's going to be, what's the first thing we do? Go back and look at our previous thing. Where was it? There it is. Okay. Where that second derivative either is 0 or does not exist. Okay? So let's first set it equal to 0. Okay? Now, what's going to make that equal 0? Is the denominator going to have any influence at all on whether that's 0 or not? No. Okay? It's only the numerator. And let me tell you this, 3 is never 0, okay?
They got different answers.
Did they?
Yeah.
Uh-oh. May have botched it up somewhere here. Let me find where I am. Thanks for catching that. Okay, it looks like I forgot to multiply through by something. It's pretty close, except for all right, let's back up and see. F prime was minus 6, x squared blah blah, 2x, yep, we got that the same, which is minus 12x over x squared plus 3 squared. And F double prime, they did the quotient rule, I think, whereas we did the, wait a minute. No, I think we did it okay. All right, let's go back and check our work here. The first times the derivative of the second would be minus 12x times a minus 2, that's a positive 24x, times the x squared minus plus 3 to the minus 3, and then times a 2x from the inside, minus 12 times x squared, blah, 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 okay. See, they did quotient rules, so it won't quite look the same. Oh, goodness gracious. I left off. No, I didn't. I had it in there. 48x squared minus 12 over that, and that's over cubed squared multiplied by another one. Oh, that's a 36 there. 12 times x squared, yeah, 36. So then exactly, let's clear that numerator out of the way. Good catch there, okay? That would be 36x squared minus 36, which is 36 times x squared minus 1. Right, okay. So, first to set that equal to 0, where is that equal to 0? The denominator doesn't contribute anything. 36 doesn't contribute anything, or 36 can't be 0. Where is that 0? X equal 1 or minus 1, is that what you said? Okay, I hope so. Okay, x equal 1 or minus 1. Those are the two places where your first derivative is 0. Is there any place where the first derivative or second derivative doesn't exist? Well, that would be, now you look at your denominator. Is there any place this is equal to 0? That's going to make it not exist, right? Any place that denominator is 0. What you think? Any place that denominator would be 0. That would be a place where this second derivative would not exist. Any place that's going to be 0? Nowhere in the world. Why? X squared can't be negative, right? Might be 0, but it can't be negative. Add 3 to it, it can't even be 0. Okay? It's going to be 3 or greater. And then you cube it, it's even greater. Okay? So guess what? No place that denominator is going to be 0. Other things we look for are square roots. There aren't any square roots. So that doesn't. Logs. There aren't any logs. So therefore, no. There's no place for this. Those are only two, you might say, places that are going, what we used to call critical numbers if they were first derivatives. We can't call them that now, but those are the two numbers of interest where your second derivative goes to 0. So now what we have to do is go somewhere to the left of -1 and do a test interval here. Okay? With our second derivative. So if you're something to the left of -1, let's say -2. -2 squared is? -2 squared is? 4 minus 1 is 3. So the numerator is going to be positive, the denominator is always positive. So this is going to be positive. We don't care what the real value is. So anywhere between minus infinity and -1, the second derivative is positive, so that means it's concave. Second derivative positive, what does that mean? Concave up. Okay? Now, let's pick something between -1 and 1. Oh, what could be in there? 0, easy one. Okay, you put a 0 in for x here, and what does this become? -1, that's going to be positive, so that's going to be a negative numerator. Put a 0 in here, and what do you have? I don't care about the value. Positive. Negative over positive is negative. That means between -1 and 1, you're concave down. Okay? Now let's go beyond 1. Okay? Pick me a value. 2, why not? We almost have done this before, haven't we? 2 squared is 4, -1 is 3, that's positive, 36 is positive. The denominator is always positive, so guess what? Concave up from there on. So from 1 to infinity, concave up again. All right, we just did it. All right, let's see how they did it now that I caught my stupid mistake, or you caught it for me. Okay, we'll erase all this. What they're going to do is begin by observing that f is continuous on the entire real number line. Now, why did they say that? Basically the same thing we said before. The only thing that would make it discontinuous is what? What would make that discontinuous? Three things you have to watch for, folks. Zeros in denominators, that makes it discontinuous. Negative square roots, or even any even root, that would make it not happen. And negative or 0 logs. We don't have any square roots, nor we have any logs, and that denominator can never be 0 because it's a squared with something added to it. Squared something subtracted from it, yeah, could be 0 then. But squared with something added to it, never could be 0. Okay, so that's the first thing. Continuous on the entire real number line, so we don't have any places that we have to say, can't even evaluate it there because the function's not there. So we're going to look at the whole number line. Okay? So, next step, find the second derivative. Well, guess what? Got to find the first derivative first. So let's find the first derivative. You rewrite it that way, and then, rewrite it like you suggested, 6 times x squared minus 3 to the minus 1, and that gives us, first derivative would be minus 6 times x squared minus 3 to the minus 2 times your 2x, which means that Jay was. All right, does anyone else come in since I called roll? Okay. We're doing example 1 on page 192, and we've done it. We're just watching them do it now. First derivative is that. Rewrite that reasonably, and I like to keep it in linear form. They like to do it in rational form, okay? Linear probably is not the best way. Minus 12x in the numerator and the x squared plus 3 squared in the denominator. So I would just as soon keep it in the numerator as well as x squared plus 3 to the minus 2. Because then the next thing we've got to do is take the second derivative. Okay? And they use the quotient rule, which is a little messy, but it's true. It's log, that's the denominator, x squared plus 3 squared, d high, which is your minus 12, minus, remember that's a minus, high minus 12x, d low, and the derivative of the denominator is 2 times x squared plus 3 times 2x, okay? All over your denominator squared, which is just, to me, a lot messier, okay? Now, here's what I don't recommend. I don't recommend you multiply everything together, just certain things, okay? I'd bring the minus 12 out front. So minus 12 times x squared plus 3 squared, okay? And then I would do the minus times minus and make it a plus, because that's a minus out front here. A plus here, and multiply the 2 times 2x times 12x, multiply those together, and that is 4 times 12x would be 48x squared. So plus 48x squared, but don't multiply them by that. Leave that separate. This is School of Hard Knocks, okay? So I don't know if the book's going to do it this way, but here's how I would do it. I would make a minus 12 times x squared plus 3 squared, and that came out to a plus 48x squared times x squared plus 3, and then divide that by x squared plus 3 to the 4th power. Now here's why I suggested doing that. Leave the x squared plus 3's in their forms. Don't distribute those, because you see here we have 1 here, 1 there, and you have 4 down here, so let's make that a 3. Okay? I hope that was okay. It's kind of quick and dirty, but that makes it, they skip steps, I can tell. Minus 12x squared minus 36 plus 48x squared over x squared plus 3 cubed. And then combine those two and you get 36 x squared minus 36. This is where I messed up before. X squared plus 3 cubed, and then factor out the 36 times x squared minus 1 over x squared plus 3 cubed. Okay, that's the one to go on. And it's pretty obvious here when you set that equal to 0 that It only happens with x equals plus or minus 1. The other question you ask yourself, is there any place this doesn't exist? No, that exists everywhere. Because the denominator is always positive, and that's the only thing that can keep it from existing everywhere. Okay? No square roots and no logs. So now, let me show you what they did. They jumped right from that expression to this expression without showing any of the work. And that's why I wanted to show the work. Okay, so I'm going to erase it now. But they jumped right to our same conclusion. Okay, there's your second derivative. And because f double prime is equal to 0 when x equal plus or minus 1, and f prime is defined on the entire real number line, they didn't say that until now, but it is, you should test f double prime. Oh no, that's f double prime, it's defined everywhere. In other words, it doesn't have any place it doesn't exist. Then you should test f double prime on the intervals from minus infinity to minus 1 to 1, and 1 to positive infinity, which is exactly what we did. And they did their little chart. They like their little charts. If you like charts, put the chart, by all means. It's good. There's nothing wrong with it. They also chose x equal -2. And all we worried about was whether it was positive or negative. It was positive there, meaning concave upward there. Okay, from minus 1 to 1, that second derivative was less than 0. Concave down from minus 1 to 1, and then past x equal 1, it was concave, x equal 2, concave up again. So we know that these are turning points for our first derivatives. It's positive here. Okay. Increasing, the first derivative is increasing up to here, decreasing past there, and then increasing again. Okay, first derivative is doing that. That means the second derivative is concave up here, concave down there, concave up there again. Okay. Now, these values here we don't call critical numbers, but they're the numbers that we use to test our intervals, minus 1 and 1. Any questions on that? Okay. The function given in example 1 is continuous on the entire number line. When there are x values at which the function is not continuous, these values should be used along with the points where the second derivative is 0 and the second derivative does not exist to form test intervals. Okay? You use the places where the function does not exist, and I would go so far as saying where the first derivative doesn't exist as well. They didn't mention that here, but you surely should do that as well. All right. They're skipping example 2. So let's go back here and do example 2. Determine the open intervals on which the graph of f of x is equal to x squared plus 1 over x squared minus 4, or concave up or concave, yuck. Concave up or concave down. Okay, real shorthand there. All right, what's the first thing you consider? The last hint gave it away. Anybody? Any place where the function doesn't exist. First, get those down while you still have it in function form. Is that defined everywhere? Yay or nay? What 3 conditions you look for to see whether it makes sense. Second? Square roots, nor any. Good. Check that one off. Throw it away. Logs, no logs. What was the other one? The simplest one. The one you ran into first. You can't ever divide by 0. Are there any places where your denominator might go 0? What you think? Oh, really? If that was a +4, I'd say I'm in complete agreement with you. With that being a -4, what we would do is factor that denominator, set it equal to 0, see if there's any values where it would go to 0. Are there any? What? Not just 2. 2 is correct. -2. If you factor that, it would be x plus 2 times x minus 2, set it equal to 0. One of those makes it -2, one makes it +2. Okay? So x equals plus or minus 2. In other words, x cannot equal plus or minus 2. So those are two values. Why is that not showing up? There we go. Okay? Two values you can never consider. So they may be portions of your test intervals now. You got it. You can't go to plus or minus 2, so you're going to have to test to the left of -2, in between plus and minus 2, and to the right of +2. You're going to have to do it. Okay? So, first determine where the function doesn't exist. Okay? That doesn't exist at plus or minus 2. All right? Then guess what we do next? What's the good Jesus answer? Take a derivative. Now, my question to you is, how do you want to do that? Do you want to do it quotient rule, which is set up for, or do you want to do a little bit of extra work at the beginning, but probably cut down on your work at the end by doing a product rule? I don't care really too much, but a little bit. Which way you want to go? Anybody? Product or quotient? I don't care much. Which way you want to go? If you got to take a derivative, you got to decide which method you're going to use. Decide. Just let me know, one or the other. Product or quotient? Second? Quotient? Is that what you said? Okay, let's do quotient rule. How does that go? You chose it, you ought to know what it is. Okay, what is it? Okay, but you start low, and then go high. Okay, low to high, so that's x squared minus 4, that's your low. And what's the derivative of your numerator? 2x. Okay, that's your d high. What follows that? Minus what? Reverse of what you said before. High d low. Okay, so that'd be x squared plus 1 times the derivative of the denominator, which is 2x. Okay, all over low. Okay, x squared minus 4 squared. Okay. Let's clean up the numerator a little bit. Now again, my suggestion, no, forget that. Okay, clean up the numerator a little bit, and I tend to want to leave the x squared minus 4 as it is, but let's put the 2x out front. I may regret that, not putting it in front, but leaving it as is, times x squared minus 4 minus, yeah, I think I will regret it. let's go on and multiply or distribute. Quite often it's good to leave those terms intact, but since you don't have one in the other one, we need to deal with it. Okay, so this will be a 2x cubed minus what? You tell me. Anybody? I got it started for you. Anyone? It's not that hard. It's just simple distributing. What would it be? Help me, somebody. I even put the minus sign there for you. Say again? 8x. Okay, now let's do the next part. Here's a minus in front of that. When you do that part, you get minus 2x cubed, right? Next part. Minus 2x. Okay? And all this is over x squared minus 4 squared. That one I almost never say, okay, figure out, go on and multiply that out. No, you don't need to. Leave it and square it. The reason I did it this way is we can simplify the numerator. How? Well, the 2x cubes disappear, which is pretty nice. And the x's combine to be minus 10x over x squared minus 4 squared. So there's your f prime of x. Okay? Now, later we'll be interested in where that's equal to 0, like we used to be. We're not interested now. All we're asking for are the open intervals on which it's concave up or down. It doesn't matter what the first derivative is doing, except you also have to note any places where this doesn't exist, but where that doesn't exist are the same values where your function didn't exist, at plus or minus 2. So those are still in there. You still can't use plus or minus 2. Well, of course you can't, because you couldn't up there, you can't down here either. Okay? So what do we do next? We're looking for concavity, not extrema. So guess what we do next? Anybody? All right. 10 o'clock scholar. Okay. Malcolm's here. Okay. All right. Guess what you do next? Anybody? Looking for concavity. What have you got to do? Take a derivative of the first derivative, which means your second derivative. So y'all may want to use the quotient rule again. I don't particularly, so I'm going to rewrite this as minus 10x times x squared minus 4 squared. Okay? Oh, to the minus 2, sorry. Got to do it correctly if you're going to do it. Okay? Now, let's take the derivative of that. F double prime of x is then going to be, using product rule, what would that give you? Did I hear a minus 10x? Thought I heard something. Maybe I did. Maybe. Second? Yeah. Second? Okay. She's doing several things at once. I'm going to do it one step at a time. The first, which is minus 10x, times the derivative of the second, which is minus 2 times x squared minus 4 to the minus 3 power times chain rule 2x. Buy that? I'm going to go back and clean it up like you were going to. Okay? That's just the first part, though. The second part is, normal would be a plus, but you got a minus there. Derivative of the first, which is minus 10, times the second, which is just x squared minus 4 to the minus 2. All right. More they come, the worse they come. I mean, nothing. What is this? Ryan's here. Ooh. I didn't want any incident reports in the class, okay? Be very careful doing that. All right. So that's the product rule, okay? The first times root of the second plus the second times root of the first. We've done it, okay? Now, we got to clean up that mess. So let's write it with numerators and denominators now. In the numerator here, we've got a minus and a minus. That's going to give us a plus. It's a 10x times 2 is 20x times another 2x is 40x squared. And the denominator is just the x squared minus 4 cubed. The next term is pretty simple. Minus 10 in the numerator and an x squared minus 4 squared there. Well, what we got to do is common denominator, so we're going to have to multiply this by another x squared minus 4 and multiply this by an x squared minus 4. Okay? Now, running out of room rapidly, so this gives us a 40x squared minus 10x squared minus a minus is plus 40, right? Over x squared minus 4 squared. And when you combine like terms there, you get 30x squared plus 40 over x squared minus 4. That's a cube. Y'all let me get away with that. That's a cube there. Okay? Now, it's nothing too special, but I like to factor out a 10. 10 times 3x squared plus 4 over x squared minus 4 cubed. All right. There's your second derivative. I didn't even write second derivative down. I must have erased it. Oh, there it is. Okay, there it is. All right. So what I'm going to do is erase most of this, if that's okay. And I'm going to start by erasing this right here. Okay? Because what I want to put in its place is what the second derivative is. Goodness, I must have forgotten to set my clock ahead. Okay? All right. Here's Devin. It's not just aimed at you. The third one in just the last few minutes. Okay? All right. Devin's here. Good to see you. Okay. And what was that? Okay. All right. All right. I'm going to write down what my second derivative is. And I factored, you don't have to, 10 times 3x squared plus 4 over x squared minus 4 cubed. Now, I hope that's what they got. Y'all keeping track with me? Hey, look at that. They did, didn't they? All right, so I'm going to go back to erasing now because we need more room. I'm going to leave the first derivative up there even though I don't really need it, but it's kind of out of the way. And I'm going to erase all the rest of this. just because it was so messy. Okay, but you can see it all if you go and watch when this gets uploaded. And by the way I'm doing things now, usually it's the end of the day before I get this into the playlist, because these classes come back to back to back, and so I don't have time to upload to the playlist until around 5:30 to 6ish. So if you're looking for them, it'll be after that, and then they'll be out there on Blackboard through the YouTube videos. All right, so there's your second derivative. Now, what was the question here? Where is this function? Determine the open intervals on the graph where it's either concave up or concave down. Okay? So what are the things we concern ourselves with? That's ending a sentence with a preposition, which is not good in English class. But fortunately, this is math class, okay? So what do we focus on? Very similar to what we did with our critical values. What are those two things we investigate? Where the second derivative is either 0 or does not exist. Now, the only place it does not exist is exactly where the function didn't exist, at x equals plus or minus 2. So that's still an issue here, so we're still going to deal with that. Okay? So the other one is where it's equal to 0. Where is the second derivative equal to 0? Well, certainly not the denominator doesn't contribute anything. That tells you where it doesn't exist. If you set that equal to 0, obviously 10 can't be 0. Never. Not in this universe. Okay? And this thing right here, can that ever be 0? That would require 3x squared to be minus 4, wouldn't it? And that would mean x squared would be minus 4/3. Can x squared ever be a negative number? No. So there is no place this will ever be 0. So our only two discriminating points are plus 2 and minus 2. So we need to look to the left of minus 2, in between plus and minus 2, and to the right of positive 2. So pick me a test value to the left of minus 2. Anyone will do. Left of minus 2. Negative 3 sounds like a good one. So let's plug in f double prime of negative 3. And I'm really not interested in what the value is. I'm interested in what the sign is, S-I-G-N sign. So this will be 10 times 3 times negative 3 squared is? Negative 3 squared is 9 plus 4 over negative 3 squared was again 9 minus 4 cubed. Okay? Now, let's just do an analysis of this. I don't care what the actual value is. This thing up here is always, all right. All right. Joy, right?
You said x squared can't be negative,
Second?
You said x squared can't be negative?
Well, what do you think? Can x squared ever be negative?
I thought the square root was going to be negative.
What's under the square root can't be negative. That's true. But what we're doing is evaluating this thing, the second derivative, at x equal negative 3. Well, 10 is 10, 3 is 3, and negative 3 squared is 9, which is not negative, plus 4. So then I said that numerator, can it ever be? That may be what you heard me say. Can that numerator ever be negative? It has only positive numbers in it, right? Okay. So how about that denominator?
It looks positive.
That's going to be positive because 5 cubed. So this is positive, numerator positive, denominator is positive. This whole thing is greater than 0. What does that tell you about concavity? Up. It's concave up. So this function is concave up. I like to just do this from minus infinity up to minus 2. Okay? Now, we investigate a point somewhere between minus 2 and plus 2. Pick a value between minus 2 and plus 2. What am I doing? I don't know. All right. Did you pick one? What? Something between minus 2 and plus 2. Okay, negative 1 is certainly in there. You like to work too hard. I'm way lazier than you. I'm even lazier than that. 0! I love doing 0. Okay. That's doing nothing or pretty close to it, isn't it? So f double prime of 0 is going to be what? The 10 stays a 10. 3x squared becomes a 0. That becomes a 4. It stays a 4. But what does that denominator become? When x equals 0. And it would have worked just as well for minus 1 or 1. They're both easy. So I was just making fun. But whatever. What's that denominator become? When x equals 0? Help me, somebody. What does that denominator become when x equals 0? Negative 4, you said? Cubed. And what's that going to be? I don't care about the number. I want the sign. S-I-G-N. It's going to be negative. And if the numerator is positive, the denominator is negative, that means this is negative, less than 0. So that means you're concave what? If the downward, anytime you're between minus 2 and 2. Okay? And then we need one more test point. Where might that be? To the right of 2. What value? Second? Okay, but what value? Second? 3. I like 3, okay? F double prime of 3 will be, there's the thing. 10 stays 10. 3 stays 3. 3 squared becomes 9 plus 4 divided by 3 squared is 9 minus 4. We've seen this before, haven't we? Cubed, and what does that tell you? Always, always positive. Which means what about the concavity? Concave up, that's supposed to be a C, concave up from 2 to positive infinity. Perfect. Okay? See how the book did? Concave up, concave down, concave up. Perfect. Now the difference here is it's not a continuous function because we knew from the very beginning that x cannot equal plus or minus 2. So you have vertical asymptotes at minus 2 and plus 2. So the function doesn't even connect there. That's what we got from. Okay? Now, any questions on this? That was example 2, page 193. Okay? Now, the next topic is points of inflection. And we're about a little over halfway through the class. Is this a decent time? I know for some of you it's not, because you just got here, but is this a decent time for the rest of us to take a break? Okay. I'm just playing with you. Huh? All right. So let's do a quick break here. Try to keep it. All right. So we're going to pick up again at points of inflection. And if you've been paying really close attention, you probably have guessed what they are. Your extrema are where your first derivatives change direction. If the first derivative was increasing, became 0, and then started decreasing, an extreme value. That could have happened where the first derivative did not exist, as long as it changed direction. Okay? But however, the first derivative could have gone to 0 and then kept going in the same direction. That's not an extreme value. Okay? Well, points of inflection are sort of, for your second derivative, a lot like your extreme values were for your first derivative. Okay? They are places where the second derivative changes signs, or possibly where they don't exist. Well, they either go to 0 or don't exist, but they change sides there. If the tangent line to a graph exists at such a point where the concavity changes. Now, that's a weird way of saying it, but it's sort of true. If the tangent line to the graph exists at such a point as where the concavity changes, then that point is called a point of inflection. Okay? So here's what. Obviously concave up here, and obviously concave down here. There is a point there where the tangent line does exist. Now notice that earlier description they gave of it. The tangent line where it's concave upward is always below the curve. The curve is above the tangent line. And where the curve is concave downward, the curve is below the tangent line. So at these points, the tangent line crosses the curve, okay, at that point. It's below it here, above it there, so it actually crosses the curve. So that's called a point of inflection, okay? Here, too, we're concave down here and concave up here. Another point of inflection, okay? However, in this one, you have a concave up here and a concave down here, but the tangent line does not exist there, okay? Well, wait. They're saying that is a point of inflection, okay? Whereas this is saying not. It says 3 types of points of inflection are shown here. Okay. They say the tangent line exists, it's just not defined. The slope is not defined. I thought they were meaning, so if the tangent line exists, whether the slope is defined or not, then then it's called a point of inflection. Here's where it would. I was going to say a cusp. Yeah. I think that would be excluded by this definition. The tangent line does not exist at a cusp, where it comes up and the point goes down. There is no tangent line at that point. It's going this way here, that way there, but there is no tangent line at the cusp. So those are not considered points of inflection. This would be, and that would be. The tangent line exists. The slope doesn't exist, but the tangent line exists. Those would all be points of inflection. Okay? And at every one of those, the tangent line crosses the function. Most other places, tangent line is tangent to the function. Doesn't cross, just kisses there. Here, the tangent line actually crosses. Okay. So here's your definition for a point of inflection. Let f be a function that is continuous on some open interval, and let c be a point in the interval. If the graph of f has a tangent line at the point c, f of c, then this point is a point of inflection of the graph of f when the concavity of f changes from upward to downward or downward to upward, okay, at that point. To locate the possible points of inflection, you can determine the values of x for which the second derivative is equal to 0 or the second derivative does not exist. Just like we did for first derivatives on your extreme values, you do the same thing here, critical values. This is similar to procedure for locating relative extremity. Okay, so here's the theory that goes with that definition. If C, f of C, is a point of inflection on the graph of f, then either f double prime is equal to 0 or def double prime does not exist. Okay? That is a point of inflection if either of those is the case. No, I'm sorry. If it is a point of inflection, then either of those is the case. That doesn't mean that f double prime could be 0 or doesn't exist, and that means guarantees it to be a point of inflection. Remember, it doesn't go both ways. This is only one way. If this is a point of inflection, then the second derivative either has to be 0 or it doesn't exist. Same type of reasoning we had on the other. Here's example 3. All right. Determine the points of inflection and discuss the concavity of the graph of f of x is equal to x to the fourth minus 4x cubed. How would you begin the process? Take a derivative. Excellent idea. F prime of x is equal to what? 4x cubed minus 12x squared. Perfect. Okay. Now, all the problem asks for is determine the points of inflection and discussing the concavity at those points. This doesn't say anything about extreme values. There's just no reason here to stop and look for your critical values. No reason at all. They didn't ask for it. Later problems will ask for everything. This one isn't, so let's continue. What would you do next? All right, time out. There's one thing we probably should have said first. Is there any place where any value x that is not defined in that function? Any place where the graph would be discontinuous in that original function? No, it's a polynomial function. It's defined everywhere. You always need to check that because there is a place that would be the case. You've got to exclude that from all your other considerations as well. This is polynomial, fine. So what do we do next? Second derivative, f double prime of x. And what would that be? 12x squared minus, what's that again? 24x. Now, what do we do with that? Okay. Why would we want a factor? Because we're going to set it equal to 0. The two things we're interested in for that second derivative, the points of inflection, we want to see any places where they're 0 or don't exist. So the first thing we're going to do is set it equal to 0, and now we factor so we can solve that equation. And how would that factor? 12x times x minus 2 equals 0. Now what does that tell us? Where would that be equal to 0? Either at x equals 0 or x equal 2. Okay? Those are our two candidates to be points of inflection. Doesn't guarantee they will be, but those are two candidates that might be points of inflection. Is there any place where that second derivative does not exist? No, it exists everywhere. That's a good polynomial function. It exists everywhere. So these are the only two possible candidates for points of inflection. So what do we better do to determine if they are, especially if we're going to discuss the concavity? Let's do a test point where At 1 would be good. That would be in between the two. So let's do f double prime of 1. And you know, I just about as soon do the factored form. That would be 12 times 1 minus 2. Now, all we're interested in, we're not interested in the value, we're interested in the sign. What is the sign of that? Negative. So this is negative. Okay, less than 0, which implies that what does that imply? You tell me. What does a negative concavity tell you? Second? I'm sorry. A negative second derivative tells you downward? Is that what you... Yes. This is concave down. And where is it concave down? Zero to 2. Okay. So it's concave down 0 to 2. That's one possible test point. Do we have any others? Anybody? Second, -1 would be good because it's outside of that, okay? So let's do f double prime of -1. And again, I sort of like this form. So it'd be 12 times a -1 times a -1 minus 2, okay? Now what can you tell me about that one? That's positive because this is a minus, that's going to be a minus. So this is going to be greater than 0. And what does that tell you? It's concave up. Where? Okay, negative infinity to 0. Always start with the lowest one first. Okay? And what else? Are we through? No, we're not.
3.
Okay, let's try 3. F double prime at 3. Okay? And at 3, 12 is still 12. X is now 3. And this is 3 minus 2. What can you tell me there? This is positive. So that implies what? Concave up from where? 2 to positive infinity. Okay. So, what can you conclude? Are these inflection points? Here to the left of 0, it was concave up. To the right of 0, it's concave down. Yeah, that's an inflection point. Or at least that's the x-coordinate of the inflection point. To get an inflection point, you need an ordered pair. So how do we get the ordered pair? I know what the x value is 0. So point of inflection at x equals 0, but I need a y value. How do I determine that? Anybody? What is y? This is a good pre-calculus algebra question. What is always y? F of x. So let's go to our f of x and plug in a 0. And what do you find the y to be? 0. So it's a point of inflection at 0, 0. Okay, what would be the second one? At x equal 2. But now we have to figure out what the y value is there. What would that be? Anybody? Okay, 2 to the 4th is Somebody.
16.
16 minus 4 times what's 2 cubed?
8.
4 times 8 is 4 times, 4 times 8 is 24. No, it's not. 32. Okay. And 16 minus 32 is negative 16. So there's the other negative 16. So determine the points of inflection. There's one, and discuss the concavity. Concave up to the left of 0, concave down between 0 and 2, and concave up again between 2 and infinity. There it is. Okay, I was trying to find it. So we've done it. They are actually going to draw a picture, which will be nice because I don't have to. Okay, so let's do this. Let me erase this. Any questions before I erase it? Okay, have we done everything they ask? I think so. They'll do a little bit more. Differentiating twice produces the following. Here's your original function. F of x is equal to x fourth minus 4x cubed. Differentiate once, you get 4x cubed minus 12x squared. Differentiate one more time, you get 12x squared minus 24x, which you could write and should write as 12x times x minus 2. Okay? The reason to factor because we're going to set it equal to 0. Actually, we'll first see, is there any place it doesn't exist? No, it exists everywhere. It's a good polynomial function. So now we're interested only in where it's equal to 0. You determine that the possible points of inflection occur at 0 and 2. Notice there's still possible points of inflection here. You can't confirm it until you do the test points. By testing the intervals determined by these values, you can conclude they both yield points of inflection. Okay? A summary of that testing is shown here. To the left of that, concave up, just like we saw. To the right of that, it's concave down, just like we saw. And between 0 and 2 is concave down, and to the right of 2 is concave up again. Okay. Now, the interesting thing here is this point of inflection would also have been a critical value. I know that because the first derivative would have been 0 there. But it wouldn't have been a maximum or a minimum, because it looks like it's going to be a minimum here, but then it looks like it's going to be a maximum there. So it was neither an extreme value, but it is a point of inflection. Concave down here, and then somewhere here it changes. Obviously it's concave down here, obviously it's concave up here. Really hard to say exactly where it changes, except using the algebra, and it tells you that was exactly at x equals 2. And that's the point of inflection because it's concave down before, concave up afterwards. And you do wind up with one extreme value there. Okay? It's not all that usual to have more points of inflection than you have extreme values. Most of the time you'll have probably more extreme values than points of inflection, but that's not always the case. In this case, more points of inflection than you have extreme values, because those two basically merged into one and became neither. All right, does that make sense? Okay. Now, as I pointed out when we had it, the converse of theorem 3.8 is not generally true. Just because you have a second derivative equals 0 or a place where it doesn't exist, that does not mean that those are points of inflection. Just like we saw in the last thing, just because you have the first derivative equals 0 didn't give you an extreme value. Same deal here. For instance, here's a graph. Okay? Graph of f of x equals x to the fourth is shown here. You know, it looks a lot like a parabola, only it's flatter near 0 and steeper outside plus or minus 1. Okay? Now, the second derivative of this, if you take the first derivative, what do you get? First derivative, 4x cubed. Take the second derivative. Second? Yeah, 12x to the...
12x squared.
Huh?
12x squared.
12x squared, right, okay, I couldn't hear well. Okay, 12x squared, okay? And that's equal to 0 at x equals 0. Do you think that's a point of inflection? X equals 0? No, it's concave up here and concave up there. Not a point of inflection, even though the second derivative is 0. Second derivative is 0, x equals 0, but the point 0, 0 is not a point of inflection because the graph is concave up to the left and concave up to the right. It's concave up everywhere between minus infinity and positive infinity. So it doesn't have a change of concavity. In other words, the tangent line does not cross the graph. It's tangent to the graph. It is all below the graph. Okay. So just because the second derivative is 0 does not guarantee it's an inflection point. You have to test your concavity on either side. Make sense? Okay. All right. We're ready now for the second derivative test. Okay. Oh, we haven't had the first derivative. No, yeah, I'm sorry. Not that kind of test. Okay. In addition to testing for concavity, the second derivative can also be used to form a simple test for relative maximum or minimum. Okay? The test is based on the fact that if the graph of a function of f is concave upward on an open interval containing some point c, and if that f prime of c is 0, meaning it's got a horizontal tangent line, then f of c must be a minimum. Because if it's concave up there and you've got a 0 derivative there, it can't help but be a minimum because it's going up on both sides. Okay? If it's concave down, that's got to be a relative maximum. Okay? So that's much easier than going back and doing your test intervals on your first derivative. Just take the second derivative, see what the value is. If it's positive, then it's a minimum. Negative is a maximum. Similarly, if the graph of function of f is concave downward on an open interval containing c, and if f prime of c is 0, f of c must be a relative maximum. Because if it's c is a critical value, first derivative is 0, and it's concave down there, that's got to be a maximum. Okay? So here's second derivative is positive here. C is a horizontal tangent line. That's got to be a relative minimum. Horizontal tangent line here. The second derivative is negative. It's got to be relative maximum. Does that make sense? No way around it. And it's much easier than doing test values. Okay? Just do that second derivative. See what its value is there. So here's theorem 3.9, second derivative test. Let f be a function such that f prime of c is equal to 0. That means it's a critical, c is a critical value. Okay? And the second derivative of f exists on the open interval containing c. If it exists, that means you can evaluate it. Okay? If that f double prime of c is positive and f prime is 0, that has to be a relative minimum. Concave up with a horizontal tangent line, got to be a minimum. If the f prime of c is negative, meaning concave down, and it does have a first derivative of 0, that means it's got to be a relative minimum. That's c f of c. If f double prime is 0, the test fails. You can't tell whether it's what it's doing there. Okay? So you have to then do. Let's go back for a moment. This one. First derivative is 0 at 0. Second derivative is 0 at 0. Okay? If that was positive, you say that's a relative minimum. Well, it's still a relative minimum but the second derivative is 0, so it doesn't guarantee it, then you have to do test intervals. Okay? But on these, when the second derivative is positive or negative, then it guarantees. So second derivative of 0 is neither greater positive or negative. The test fails, you have to do. It could be a relative maximum, it could be a relative minimum, it could be neither. Such cases you have to use the first derivative test, which means do your test intervals. Do a value on either side of that and see what the first derivative is doing. Make sense? All right. This is example 4. And by the way, you can go to larsoncalculus.com for an interactive version of this type of an example. Okay? It says find the relative extrema of f of x equal minus 3x to the 5th plus 5x cubed. Okay? We want to find the relative extrema. I thought we did this back in the last section. We did, but we're going to do it more quickly, easily now. So what's the first thing we're going to do? Take a derivative. F prime of x is equal to negative 15, second, x to the 4th, plus 15, x squared. And guess what we're going to do with that? Second, we are ultimately, so we can go on and do that if you want to. Second derivative of x is, f with respect to x is negative 60 x cubed plus 30 x squared. Okay? 30x, I'm sorry. Don't know where my brain is today. Oh, it didn't take. There we go. All right, 30x. All right. We've taken those derivatives. What are we going to do with them? Well, we're looking at relative extrema. So what are we interested in? What's equals 0? And what is equals 0? Okay, now that gives you points of inflection, or possible points of inflection. Second? Plug it in. Plug what in? What point? Yes, we got to find our critical numbers. How do we find our critical numbers? Where the first derivative is what? Either equal to 0 or does not exist. Let's deal with it. Does it not exist anywhere? No, that's a polynomial. It exists everywhere. So throw out the do not exist. Let's find where they're equal to 0. So what would you do first for that one? Factor, and what would that give you?
15.
I would factor out the minus 2. Minus 15 x squared times x squared
Minus
1. Okay? And set that equal to 0. Okay? What would be your critical values? X equal 0, x equal 1, and x equal negative 1. Those are 3 critical values. Now this one at 0 happens to be a double critical value, but we don't mess with that. It's just a double root at x equals 0. Okay. Now, so we got 3 things to deal with. How are we going to deal with those? To determine whether they're relative extrema or not. Say again? Did I hear plug it in?
Yeah, plug it in.
Say again? Plug it in what? No, you're telling me. Say again? Yeah. These are the critical points. Okay, I could call this C1, C2, and C3. We could call them, those are our critical values right there. Okay? You're absolutely right. Plug those into the second derivative and see what we get. Okay? So let's do F double prime. Which one you want to do first? Second? 1. Okay? And what do you get then? Minus 60 plus 30 equal? Say again? Negative 30. What does that tell you about the concavity at x equal 1?
It's going down.
Going down. So what must that critical value be?
Less than 0.
Say again?
What's that?
If it's going down,
Yeah, you better.
if it's going down around x equal 1, and that's your critical value, meaning your first derivative is 0 there,
Minimum.
that minimum? That must be a maximum. Okay. So, at x equal 1, we have a relative maximum. Now, we actually need, to have a point, we need the x and y values. So how do we get the y value? Plug it in what?
Original, right?
Yes, the original equation. So f of 1 is equal to minus 3 plus 5 equal 2. So it would be 1, 2. Buckle my shoe. Okay. That's a relative max. Okay. We got one. Second. Okay, which one you want? 0. Let's plug in 0. Okay. F, and what do we plug it into? Second derivative. Okay. F double prime of 0 is equal to 0. What does that tell you? What does 0 stand for? Nothing. It doesn't tell you anything. Okay. You can't determine because the second derivative is 0 there. So that means we are going to have to do test values at one side or another of 0, but you have to be inside plus or minus 1. So you're going to have to use some fractions there. Minus 1/2 and plus 1/2. Okay. So we've got to go back to the first derivative test for that. Okay, you want to do that now?
Yeah.
Okay, let's do it now. So let's do your first derivative, f prime of, and which one you want to do first? 1/2. Okay, we'll do 1/2. So use the first derivative function and plug in 1/2. It's going to be a minus 15, and what's 1/2 to the 4th power? 1 over 16. Okay, plus 15, and what's 1/2 squared? 1 over 4. Okay, who wins there? Okay, so this is minus 15/16, and this is plus 15/4. 15/4 is something greater than 3. This is just a little bit less than minus 1, so the 3 wins. Right? So this is going to be positive. So this is going to be positive. So your first derivative is positive here, meaning it's an increasing function coming up to 0. Okay? Increasing function coming up to 0. Let's see what it is on, oh, no. Increasing function leaving 0, because 1/2 is on the other side. So it's increasing there. Let's see what f prime is at negative 1/2. That would be a minus 15 times negative, oh wait, no, that's positive. That's 1 over 16 because you're raising it to an even power, right? Okay. Plus 15 times what? One-fourth again, folks. And that's greater than 0 again. So that means coming in, it's a positive slope. Going out, it's a positive slope. Guess what that means? That's not an extreme value. It's positive going here, positive leaving. First derivative. So that means at 0, it is not an extreme value. Not relative maximum or relative minimum. One more to check. Negative 1. And we plug this in what? Which one? We already know what it is there. Well, we don't maybe yet. Yes, we do. That's how we got your critical values. Second derivative. So f of, is it minus 1, right? F double prime of minus 1 is equal to, this requires just a little more thought, not a lot more, positive 60, negative 30, which tells you what? This is greater than 0, which means if the second derivative is positive, what does that mean? Concave up. And if it's concave up at a critical value, what does that mean? That critical value has to be, it's concave up at a critical value, that means it has to be a minimum. Absolutely. So at x equal negative 1, it's a relative minimum. Okay? Now, we need the actual point there, so let's plug in x equal negative 1. Where do we plug that in? Say again? Where? Where do we plug it in? The original function. F of minus 1 is equal to what? Positive 3 minus 5, which is negative 2. So that's at negative 1, negative 2. It's a relative minimum. And at 0, 0, because that's what the value is, it's a point of inflection, true, but not an extreme. Not an extreme at 0, 0. It is a point of inflection, but it's not an extreme. Point of inflection because the second derivative was 0 there, and what we didn't check to see if it was, but we really already determined it was, we already said it was a positive derivative coming in, positive derivative leaving, so it has to be concave down here and concave up there. Okay? So, okay. What it said, find the relative extrema. The only two. 1, 2, relative max. Negative 1, negative 2, relative minimum. Okay. The third place where the critical value gave you neither a relative minimum or a relative max. Did give you a point of inflection, but not the other. All right. Now, want to watch them do it? Can I erase, or you want it longer? Okay. Begin by finding the first derivative. Yay, that's what we did. Minus 15 x fourth plus 15 x squared. Factor out I would have factored out a minus 15. They factor out a positive 15x squared and leave you 1 minus x squared. Okay? From that derivative, you can see that x equals -1, 0, and 1 are the only critical numbers of f, and the reason for that is the function is defined everywhere. Its first derivative is defined everywhere. Okay? So those are your 3 critical numbers. By finding the second derivative, which is minus 60x cubed plus 30x, and that factors to be, and again, in my mind they did it backwards. I would have factored out the minus sign too, but 30x times 1 minus 2x squared, you can do it that way. You can apply the second derivative test. First, you'll put in x equal minus 1 there, and you get that the second derivative is positive, which means it's concave up, so that must be a relative minimum. If you plug it in 0, you find out second derivative is 0. That doesn't tell you beans, okay? You don't know if it's relative minimum, relative max, or neither. The test fails, okay? And then when you plug in x equal 1, you find out it's negative there, so that gives you a relative maximum. Okay. Now, what's that? Okay, they just skipped the other stuff. They just said this is what it gave you. We had to plug it in to get our answer. If you have a table already set up for you, you don't have to do it, okay? But guess what? I'm not going to give you a table already set up for you. You're going to have to fill in the numbers. Okay. Because the second derivative test fails at 0, 0, you can use the first derivative test and observe that f increases to the left, increases to the right, so therefore it's neither a maximum or a minimum. Okay. So here's your values, your critical values for here, where the first derivative is 0 here, first derivative is 0 there, first derivative is 0 there. Okay? Here, relative minimum, because second derivative is positive. Here, undetermined, because the second derivative was 0 here. Here, second derivative is negative, so therefore it has to be a relative maximum. So go back here and plug in a value, say at 1/2. Here it's a positive. Negative 1/2 that gave you positive. Positive 1/2 gave you positive. It's not changing its sign there, so it's not a relative maximum or minimum. But because of the nature of this, you see it's concave down here, concave up there, so it does make a point of inflection. Which you can also tell by the graph, your tangent line crosses the function. Here the tangent line does not, so that happens to be a minimum. Here it doesn't, so it happens to be a maximum. Here it does cross, and therefore it's a point of inflection. Okay. Any questions? All right. Just a few things to note here. This is an odd function, meaning it's doing exactly the opposite on the left as it is on the right. So therefore, that almost guaranteed you this is not going to be a maximum at 0, 0, because it's an odd function. So if it's increasing here, if it was negative here, it's going to be positive there. So it can't be a relative extreme minimum or maximum. But that was looking at it a little bit differently. But whatever it's doing on either side, it's always in the opposite direction. So it is an odd function. Okay. Any questions? Which one? Okay. When I went to, yeah, I had to erase it to show what they did. Sorry. Okay. All right. That was example 4. And that was the last example in the section. So homework exercises here, do 2 3 is at calcchat.com. Do any of the odds 5 through 15, they're all at calcchat. 13's at calcview. Do any of the odds 17 through 31, they're all at calcchat. 17's at calcview. Do some of the odds 33 to 43, they're all at calcchat. 37's at calcview. Do either 45 or 47, they're both at calcchat. You can explore doing 49, it should be at calcchat. You can do 51, it should be at calcchat. You can do either 53 or 55, they're both at calcchat. 53's at calcview. You can think about doing 57, that should be at calcchat. 59 should be at calcchat. 61 should be at calcchat. 63 should be at calcchat. And then you can do any of the odds 65 through 67. Either 65 or 67, they should both be at calcchat. 69 or 71 should both be at calcchat. 73 should be at calcchat. And 75 or 77, they're both true false. You should be able to find those at calcchat. And then there's a proof number 79 should be at calcchat. Now, 3.5, I have a little bit of a problem with, okay? It's not that it's difficult or thing, it just, okay. All right. Let me take that back a little bit, okay? It says limits at infinity, okay? As opposed, well, here's my problem. Infinity is not a number. So how in the world can you have a limit somewhere that's not a number? But there is a sense that you really do, and let's just sort of go through this, but you're not going to be responsible for this on the test, I don't think. I'll have to check and see, but I don't believe you will be. Let me discard this, and let's go to 3.5. And we're going to go through this pretty quickly because it's really stuff you've already done before, okay? I'll give you just a couple of hints on it. How are we doing time-wise? Okay. We got about 15 minutes. Okay. We're still in Chapter 3, Applications of Differentiation. Okay. And 3.5, I guess the thing I have, limits at infinity, there is no, there's no point at infinity, so what do you mean by that? Well, limits as you get progressively larger and larger, do you have a limit of your function? So we'll determine finite limits at infinity. That kind of makes sense, a little bit anyway. Determine horizontal asymptotes, if any, of a graph of a function. Yeah, that makes sense. Determine infinite limits at infinity. That's the part that to me doesn't make any sense at all. Because if it's infinite, how can it have a limit? I mean, it doesn't have a limit. That's what being infinite means. So I understand what they're saying, but it's sort of a weird way of saying it. Okay. So this section discusses what we call the end behavior of a function or on an infinite interval. Okay? And the only reason I even paused to do this is the stuff you should have done in pre-calculus algebra, and this is just reinforcing. If you've got a function 3x squared over x squared plus 1. And the end behavior, which means what's happening to this function is x gets very, very large positively or very, very large negatively. Well, obviously, if x gets very, very large, yeah, this is going to dominate because that's where your x is. Down here, this is still going to dominate because what's adding 1 to a very, very, very large number going to do? It's not going to do much. Okay? The very, very large number. So basically what you do, look at the ratio of the leading terms. Leading term of the numerator, leading term of the denominator. What's 3x squared over x squared? 3. That's where the function's going. Infinitely large or infinitely small numbers. Okay, it's going to 3 this way, going to 3 that way. So why make a big deal about it? That's something you should have learned back in pre-calculus algebra. Now, what's happening in small numbers? Yeah, all sorts of other things can be going on here. But for very large numbers, it's pretty clear that's going to 3 in both directions. The reason it never quite reaches 3 is you got that little 1 down there. So you have an extraordinarily large number here, but a very large number here plus 1, so that keeps the graph just under 3 because your numerator, the denominator is just a little bit larger, so it keeps the fraction just a little below that, but not much. So it's going to 3. So that makes sense, you know. Even as you say, as x is going to very, very large numbers, your value is going to 3. Okay? Graphically, you see that, but I just told you how to do it algebraically. Okay? And you can plug in numbers if you want to, and you see it's going to 3 this way and going to 3 that way. Both directions. This is the hard way. Looking at ratio of leading terms, that's the easy way. The table suggests that for f of x approaches 3, as x increases without bound to positive infinity or to negative infinity. Similarly, f of x approaches 3 is, I just said that, going to negative infinity. These limits at infinity are denoted by the limit as x approaches infinity from the left. For negative infinity would be 3, positive infinity. Just say the end behavior. Okay, is going to 3. Okay. Now, to say that a statement is true as x increases without bound means that for some very large real number m, the statement is true for all x's on the interval x greater than m. Okay? And this definition uses that concept. So if you want the formal definition, here it is. To me, it's sort of just a lot of blah, blah, blah. Let L be any real number. Okay? Whatever your limit's going to be. Okay, excuse me. Okay? Now, the statement that the limit as x approaches infinity of f of x equal to L means that for each epsilon greater than 0, there exists an m, a capital M, also greater than 0, such that any time f of x minus L, the difference between those two, are less than the epsilon you chose, they will be whenever x is greater than this m that you chose. Okay? And the limit as x approaches infinity, negative infinity, which is not a number, but of f of x equal L, that means for each epsilon greater than 0, there exists some n, think of that as negative here, less than 0, such that if the difference between f of x and L is less than that epsilon you chose, whenever x is less than that negative number. Yeah. In other words, you can keep going out there. No matter how small the epsilon you choose, you can find somewhere out there some m, you guarantee it's going to be less than that, or some n, guarantee it's going to be less than that. Okay. Even if the function does some wiggling around there, at some value m, you can guarantee that the function is always going to be within plus or minus epsilon of your L. Okay, if it's approaching that, you can guarantee it. No matter how small you choose the L, somewhere out there, you can guarantee it's going to be less than that. Okay. All right. Now, what we were just describing there were horizontal asymptotes. Okay? In the figure we just saw, this one right back here, that one, okay, the graph of L approaches the line y is equal to L as x increases without bound, okay, because the y is closer and closer to that L. The line y is equal to L is called the horizontal asymptote. And that's a horizontal asymptote with the graph of f when the limit as x approaches infinity, negative infinity, f of x equal L, or the limit is f of x as x approaches positive infinity, f of x equal L. Note that from this definition, it follows that the graph of a function of x can have at most two horizontal asymptotes, one to the right and one to the left. Most of the time they don't. It'll be the same one if it has, one. Now let me go back to this. Now, vertical asymptotes, if you remember, and this looks like it does have a vertical asymptote, whatever this is, that there probably is some vertical asymptote. This graph can never touch or cross the vertical asymptote. A horizontal asymptote, however, it can touch or cross it as many times as it wants to. It's just getting closer and closer to it. So you can touch or cross a horizontal asymptote. You never can touch or cross the vertical asymptote. They don't mention that, but it just wanted to point it out to you. Okay? Now, so here's a definition. I think we just did that. Yeah, we just did that slide. Catch where we are here. Now, limits at infinity have many of the same properties as limits discussed earlier. For example, if the limit of f of x as x approaches infinity and the limit of g of x as x approaches infinity both exist, then the limit of those, if they both exist, then the limit of the sum of those two is the sum of the limits of those two. And the limit, same thing would be different if you put a minus sign there. The limit of a product would be the product of the limits. And same thing would happen if you're going to negative infinity. Okay. When evaluating limits at infinity, the next theorem is helpful. This is theorem 310. If R is a positive rational number and C is any real number, then the limit as x approaches infinity, now remember, R is a positive rational number, then the limit of some constant divided by x raised to the r power, as long as r is any positive real number, rational number, then that's going to 0. Catch what that means. What if c was a huge number, like 7 million? Is that big enough? Just some really huge number. And this r is some positive rational number, like 0.0000001. That's an incredibly small but still positive number. Well, 7 million divided by some value x, as x is only being raised to the 0.0000001 power, that's still going, as x is going to infinity, you're soon going to pass c, okay? And you'll soon pass the umpteenth root of c. You keep going, and soon this thing is greater than that, so now it's going to 0. Furthermore, if x to the r is defined when x is less than 0, then the limit as x goes to minus infinity, if this is defined for x less than 0, then this will still be going to 0. If you have your variable in the denominator and it's getting infinitely large, no matter how large the c is and how small the r is, as long as that r is a positive real rational number, then that will work. Okay? Now, let me just show you the quick and dirty of this. Okay? If your denominator is getting large, and there's not a variable in the numerator, where is this going? The ratio of this is, as x is very large? 0. No, 0. Okay, yeah, well, it's a minus. But this is going to 0. This stays 5. So this is just going to be 5. There's nothing magical about this, This number is x. It's very, very, now when x is getting small, this can be blowing up like crazy because x can't ever be 0, so you know this problem's there. But if x is going very large, positive or negative, this thing is a very, very large denominator, a very small numerator, that's going to 0. So this is just going to be 5. Okay? So that's all you have to do. They go through all these steps, but you get 5. Is it time to go? Oh my goodness. How could it happen? And I wasn't even planning to do any homework here in this section. So we will start next time. Let me get my pencil. Where were we? We had done example 1. Thank you. We may or may not do example 2, but we'll start somewhere there. Just got.
For the second test, did we just show our work still?
I'm sorry?
For the second test, did we just show our work still?
Yeah, oh yeah, absolutely. Every test. Show all your work. Yeah. All right, good deal. Thank you.